So hello everyone, and thank you for joining us today. This is our fourth Aviva process simulation training session. And before we started, I kindly request you to keep your microphones muted during the training session. And again, if you have any questions, please feel free to type them in the chat, and we will please put all the microphones in mute. Okay.
You caught it.
Yeah, I put it in mute. Okay, if you have any questions, just type in the chat as we did in the other days, and we will answer at the end of the presentations. So Richard, I pass the floor for you. Thank you.
Thank you, Berna. All right, let me share my screen. So for today's session, we are going to be covering the economics model library. So this is going to be everything related to operating and capital cost calculations, as well as greenhouse gas emissions calculations. That's all handled through that one model library. Then we're going to be talking about our Excel add-in, which is integration capability between Excel and Aviva process simulation. Typically, it's used to extract information from an Aviva process simulation file and use it to create a custom report. But it does have two-way communication abilities, so you can also push information from Excel back into the APS file as well. So we'll be talking about that and showing how to use that, and then we're going to be finishing up the session today with a couple of advanced features that are capabilities within the software that we haven't discussed yet, such as flowsheet equations, optimization, case studies, and scenarios. So that's the agenda for today. And at the end, I'll throw up a couple slides to show where you can get some help and further resources if you need it. But otherwise, this will be the end of the sort of required sessions for the academic competition this year. This will teach you everything that you still need to learn in regards to being able to do the competition problem for this year. But we are having an optional fifth session tomorrow. Again, it'll be on reactors and reactions, columns, and custom model writing. And we're going to have that session so that if in future competitions we have requirements that involve those topics, we'll have the recordings already available for how those different features work. Okay, so with that, let's go over the economics model library. The economics model library is used for three different types of calculations. Typically, it's going to be mainly used for operating cost calculations, for capital cost calculations, which you can see summarized here, and then as well, it's commonly used for greenhouse gas calculations. Now, all of these have an impact on economics in terms of how they have an impact on a project. And they all sort of use similar infrastructure for how they are utilized within the software. And so what you're going to be seeing here today is I'm going to talk about how to go about using these models, using this library, and whether you're doing operating cost calculations or capital cost calculations or greenhouse gas calculations, the way that you go about doing it is the same from one subtype of calculation to another. They all use the same approach. They all use the same sort of infrastructure. Right, so when I go into the software, I'm going to start talking about that and showing you how that all works. But for the start, let's just have a quick overview of each of these different types of calculations and what you might find within the model library. So when it comes to operating cost calculations, we have a couple different submodels that we will utilize that calculate different types of costs that are associated with operating your plant, right? So typically these are going to be things like raw material costs, utilities costs, such as how much water or steam or fuel or electrical power that you have within your system at various points within the file. Any sort of products that you're producing, they will often have a profit associated with them. And so we can incorporate that into these operating costs by including submodels for adding those values into your calculations. All right, and then we can also do CO2 emissions costs into this as well as part of this calculation process. The way that it typically works within the software, there's a summary model. You can literally see it's called summary. This model is going to be placed on the canvas, and it's going to be a central hub that you go to that has all of the total costs associated with various calculations throughout the entire simulation. And then what you're going to end up doing from there is you're going to use these other submodels, the ones that I talked about. You're going to place those on specific models in the simulation to factor in their individual contributions to this cost, right? So all your sources may have raw material submodels on them that add up how much the raw materials cost in those sources. Your various utility streams or models that have utilities might have this utilities model, submodel included in them to add in their contributions to the operating cost. And then your products are going to have this product submodel that's going to add in how much profit you're making from your products, right? And so each of these will be on individual models, and then you'll have you that sums up each of the individual models calculations into one place that you can look at and see all of the information in one easy to reference location. All right, and so you can see this little screen grab here is what it typically looks like looking at the summary model. And there's a bunch of different total costs that are listed in this. Now, note that this summary model is also the same model you use for the central hub for capital cost calculations. So you're going to find other things listed in here other than just raw materials, utilities, and product costs, because it's also factoring in all the capital related costs as well. But this is the central area that you're going to go to see those total values. All right, and then there's also things that you can do within this, like set your global prices for various things, such as low pressure steam, medium pressure steam, high pressure steam, electricity, so on down the line. And so you can set the values here. And then a lot of times in the individual models, when you place them on the units themselves, on the models themselves, you have these also listed in those where you can change them just at that that local location, and then it'll also propagate back throughout the rest of the simulation. Remember, these are all global, so if you change it in one location, no matter where you change it, it changes it for all of the others in the entire simulation. Right. So this is the way that it operates in general, with the summary model as a central hub, and then these individual submodels with the various pieces of information. The same thing is going to work for capital cost calculations and greenhouse gas calculations, except in those libraries, we have different submodels that get placed onto models, and we also have a different hub for the summary model when it comes to greenhouse gas calculations. And you'll see those as we go through each of these slides real quick. In Aviva Process Simulation, we use a generic currency symbol that looks like this, that you see right here, to designate whatever currency you're using. So it's up to you as the user to, give value to this and say, this symbol represents a dollar. This symbol represents a euro. Whatever the case may be, it's up to you to establish that and then just be consistent throughout your entire simulation in the way that you use and reference any sort of pricing information. Okay, so for capital costs, this is going to figure out how much it costs to actually construct any one of the various models within your simulation. So it could be stuff like pumps, heat exchangers, drums, columns. You have different submodels that you can place on each of these different types of models in order to calculate their associated capital cost. Now, the thing about all of our costing information in Viva Process Simulation is that this is not meant to be a super hot, accurate, highly reliable price. This is supposed to be ballpark pricing because you're using this pricing most of the time within the software to help understand your design calculations and understand if maybe one design is better than another design based off of some general costing calculations, right? So you're going to see some values that are in the like plus minus 30% range in terms of accuracy in the calculations. And that's typically sufficient at the design level. Just be aware that this is not meant to be the type of program that you get a real finalized value that you would actually build a plant on, right? You would go to another piece of software that has more detailed costing information, is a lot more accurate, a lot higher fidelity than this. This is supposed to be general ballpark type pricing. All right, and all of our costing information is based off of literature information, so you can see what those references are in the various help menus. I have a screenshot right here of one of them, right? But all the different sources that we use for our costing information is all cited within the help documentation of the models and other areas within the software. Okay. Everything else here is pretty much straightforward in terms of the way that this capital cost calculations work and operate. The main differentiator between this and the operating cost calculations is just the fact that we use different submodels for very specific types of unit operations or equipment that we're trying to solve or trying to size. And then greenhouse gas calculations, which I don't think you're going to need to do in this competition, but if it's something that you were to look into utilizing, it also has its own submodels for different types of contributions to the greenhouse gas calculations. But there's a different submodel as well, or a different summary model as well, where all of this is summed up and added together across the simulation. So instead of using the regular summary model when using these submodels, you want to use the summary GHG submodel on the canvas to see all of the information summed up across the entire file whenever in relation to greenhouse gas calculations. Okay, so before we go into the software and look at some examples of this, I want to talk about how this works and sort of the reason why we're able to do this within the software and the way that these models tend to operate. So when you are taking these submodels here and you're putting them onto models in the canvas, you're doing something called extending the models, right? You're extending the existing models that are already on the canvas to have additional calculations that those models didn't normally start with, right? So if you think about a source model, and we're talking about operating cost calculations, they don't automatically calculate raw material costs. You take this raw material submodel and you put it on a specific source, and that extends the source so that the source is able to now calculate costs associated with the raw materials, right? So the way that you do this is one of twofold. You can either drag and drop the submodel onto the models that you're interested in, but just note it's a shift drag and drop, right? So you have this hold shift on the keyboard, click on the submodel in the model library, then drag and drop it onto the model. The other way is that you can right-click on the model, and if you come down, there's an option in the menu called submodels, where you can add a submodel or you can remove an existing one. So if you did the drag and drop method and then you needed to get rid of it, you would do the right-click, submodels, remove, and then choose that submodel to remove. All right, but when you add this on, and you'll see this when I open up an example file to look at it, when you add it onto the model on the canvas and then you open up the model's property inspector, you're going to find a new section for those economics calculations, and it's going to have the added variables that are being calculated that are associated with the submodel that you added. Right. So the idea here is that you can extend any model with any submodel. So theoretically speaking, you could take any one of these submodels, and if you wanted to, you could copy it, edit it, add in your own calculations, and then incorporate those into a model on your simulation simply by having the custom submodel and choosing it as an extension. Right. And so what's nice about this is that when you extend a model on the canvas, it allows you to use the base version of the model from the model library you're utilizing, right? So if I'm using a drum in the process model library, I don't have to worry about copying and editing that drum to put in a customization for the drum, right? I can, sorry, there's a little net around my head. Sorry about that. I don't have to edit the drum to add in my custom calculations. I can take the normal process library drum, and then I can add a submodel that has the additional calculations onto the model when I'm using it in the simulation file. All right, so it's a way of adding customization without making permanent changes to the way the model is written in the model library. Right, and all of these work that way. Every one of these types of submodels that you're adding onto the models, they are doing this. And this is what's allowing these types of calculations to occur. Now, if you were to decide to create your own submodel and use it, let's say, for example, you need to add in some additional cost calculations that aren't included in some of our submodels, you would copy the submodel, paste it, say, into the simulation model library. You'd go into its editor and you'd start adding in equations and variables as needed to calculate whatever it is that you need to calculate, right? Well, there's a couple of things when it comes to model writing. And again, if you attend tomorrow's session, the optional one, you'll learn more about model writing. So this will make more sense, right? But there are two features when it comes to model writing that are important in order to be able to make these submodels work the way they do when you extend a model. Right? So the first one's called totalized variables. Any variable that you define in a model editor window has this little column here that has like a sigma symbol inside of a circle. If you check the box, basically, if you make it yellow, right, instead of grayed out, then you are telling the model that this variable that this is turned on for can be totalized whenever you are using the totalize function in an equation, right? So here's an example of that from the economics summary model. The economics summary model has a bunch of equations that add up the individual costs of each of the individual models within the canvas, right? So if we're talking about raw material costs, the total raw material cost for the entire simulation is the summation of all individual models that have the raw material cost variable. And so we can use this function called totalize to add up every single value where this variable is being used. And so then in my utility or in my raw material submodel, when I use that on various sources, there is a variable called raw material cost, and this little symbol is turned on, which is what allows it to be totalized, right? And so that's one of the ways that we allow this sort of extension of models to occur. The other thing that we have to do is there are going to be variables that we define in our submodel. So this is the raw material submodel that you're looking at this window for, right? This is the model editor. These are the variables in that raw material submodel. Some of these variables are meant to come from the model that you place this submodel on. So when you place the submodel, it's going to pull those values from the quote parent model, the model on the canvas, right? So if I add this raw material submodel to a source on the canvas, the idea is I'm pulling my mass flow rate and my volumetric flow rate from the source, and then I'm using it in the submodel to calculate price per mass, price per volume, raw material cost, and anything else in the submodel, right? So there's this up arrow here that needs to be turned on and checked to make it yellow, right? To be able to pull this specific variable from the thing it's attached to. If I didn't check this box, right, if I didn't turn this arrow on, when I put the raw material submodel on the source, it's not going to know what the mass flow rate is or the volumetric flow rate. Those values are going to be blank, and it's not going to be able to calculate anything, right? It's the fact that this is turned on that tells the submodel, get it from the source model on my canvas, right? So that's the idea. Now, if you're going to create your own submodel, right, for some calculations, right, whatever it is, even if it's just taking one of these and modifying it, when you add an equation and you add variables for that equation, you're going to have to make sure that you account for those variables properly for whether they're going to be totalized or if they need to pull values from the model you're adding it to, right? So this is two capabilities that relate to model writing, which again, we're talking about tomorrow as part of our optional stuff. You shouldn't have to do much model writing or any model writing in this class, or in this competition. But if you want to do this, you're going to need to be aware of these things in order for your customized submodel to work properly. All right, so with that said, let's go over and look at some examples. I have an example here. This is actually one of our training exercises, and it uses the economics library to do some operating cost calculations. And so I have the summary model here, that's this model, that I placed on the canvas. And when I look at it, it's adding up my utility costs, my operating costs, and yeah, so it's mainly just utility costs that I have in this file right here, right? And so all my operating cost is associated with my utility cost in this regard, right? And so when I look at this, it's pulling all of this information from the various places in my file where I have added this utility submodel, right? So if I look around, I look over here, I can see there's, no subsection related to economics, right? And I look here, right? So here has economics, right? I look here, nothing related to economics, right? So not every single model in my simulation is going to have the economics calculations happening. It's just the ones where I add these submodels onto, right? And if I go through this, I can find all the different instances where I've added different economics models. And so, yeah, this was one of them, right? So I added the utility submodel here for the electricity consumption within the pump, right? And so the electricity has a certain cost per value, in this case, million BTUs, right? And that gives me my electricity cost, right? If I come to here, right, this is again, utility submodel, but it's using low pressure steam. So this is the cost of low pressure steam within my file. It's that much. Again, we're assuming dollars in this case per pound. And so based off of how many pounds an hour we have, right, it's calculating the individual cost of this utility at this one location, right? And then the economics summary model is just adding these values up across the entire simulation. All right, so this one here was 335. This one here is 1.6. So if we just take those off of here, we have a little less than $500 an hour still spread out through other utilities models within this simulation. I'm clearly not showing every single utilities model, right? But you get the idea. And the way that we added these, I'll actually add the raw material one here to this feed. You hold shift, drag, drop. You can see it says add submodel of this type to this feed. We let go. Now we come in, we can see here's the economic information. And right now, it doesn't have any cost because I haven't provided it a cost per pound, right? So it's going to use the mass flow rate against whatever value that I've set here. But if I said, I don't know, it's $20 a pound, right? It calculates a value, gives me my total raw material cost here. And now that gets added up across the entire simulation. And you can see I have a total raw material cost here. And then that gets added up for the total of all the operating costs, all right, which is just this plus this right now. All right, so this is how it works. It's pretty straightforward. You can see some of these other areas that I was talking about where you can set some prices or see some other individual costs. There's a couple more parameters that you can manipulate here to change the way that the cost calculations are happening. It's pretty straightforward. So this is an operating cost example.
Yeah.
Okay, that's an operating cost example. Here's an example, and this does come from the examples folder. This is one that involves renewables calculations, right? And so when we look at this one actually has economics related calculations for utilities and some capital cost calculations. So there's a little bit of everything going on here, as well as greenhouse gas calculations. Right, so we can see that as well. And if we went through these various models, we would probably find the different economics submodels where these calculations are occurring, right? So here's an economic submodel that's used for the capital cost of the solar farm here. Here's one capital cost of the wind farm. This one here has both utilities costs for the electricity that's being created through the generator. So this generator, like we talked about yesterday, is supposed to be representative of any other type of external source of power that may be being supplied into this grid outside of solar or wind. All right, so that's the economics related to that. And then there's also greenhouse gas calculations associated with this. And you can see here it's natural gas, effectively. That's what it's using as the basis for these calculations. So economics model library, it's rather straightforward. It's really just about these summary models and individual submodels that you will add as needed to different models on your simulation, right? And then they get summed up across the entire simulation in these summary models. Right? Okay. The next topic. Okay, the next topic we're going to talk about is the Excel add-in. So the Excel add-in is an integration between Excel and Aviva Process Simulation. It typically is used to create custom Excel reports, output reports. It's one of the few ways of getting external results out of Aviva Process Simulation. And so you've seen in prior sessions, I've shown some standard reports that we do have that are available, but they're limited to certain types of output, like the stream process report. I showed tables that can be exported to Excel. I've also talked about some other types of miscellaneous calculations like heating curves, phase envelopes that can also be exported to Excel, even though I didn't show them. But really, outside of those things that I mentioned right there, there's not a whole lot of other information that's sent out of the software. Most of the results are within the software itself, such as variable references and just your various property windows where you go and enter information as much as you can get information, right? So when it comes to creating a report uh, outside of the software, this is the main way of creating your own custom report outside of the software. There is no one-click button like there may be in other software that just dumps everything from your file into an external report. So you will have to use this to create any sort of report that you want to have outside of the software. Now, the thing that's nice about this is that it doesn't require any coding. Right, so typically a lot of times with these integrations with Excel, you have to understand a little bit of Visual Basic or some other similar coding language in order to be able to extract and write information back and forth between the software program and Excel. But with Aviva Process Simulation, it uses functions, essentially, like the summation function or the average function, those different functions that you would normally use in your cells when you're writing equations. It uses the same thing here. We have our own Aviva Process Simulation functions. They actually go by the old naming convention of SimCentral, so you'll see that a lot when we're using this. Right? But it's the Aviva Process Simulation functions that are used to get the information that you're interested in. Right. Now, there are a couple of things to be aware of when you're going to use this. One, you need to have Aviva Process Simulation open in the background. So the software itself, I have a simulation file open right now, but you don't have to have a simulation file open. You also don't have to have the simulation file open that you're using in the Excel report. Right, so it could literally be no simulation file and just the software open, and you would be okay to go. But you have to have the software open. Otherwise, you will get errors when you try to use the functions or try to use any of the capabilities related to the Excel add-in. The other thing that I've seen many times is that this functionality works best when you have one and only one copy or workbook open of Excel, right? So you want to make sure that you don't have multiple Excel workbooks open down here. It's just one workbook. And you also want to be careful if for some reason Excel doesn't close properly. You want to make sure any instance of Excel running in the background is all closed as well. You just want one copy, one instance, right? Otherwise, you can also have connectivity issues between Aviva Process Simulation and Excel when you're trying to utilize this, right? But assuming you have APS open and you have one workbook open, you should be good to go with using the Excel add-in, right? Now, when you install Aviva Process Simulation, your Excel will automatically have this tab here for Aviva Process Simulation related features with the Excel add-in. Right, so this automatically gets installed to Excel when you install Aviva Process Simulation. If for some reason you do not have this tab, or you are unable to use any of these features, or the functions aren't working properly when you try to use this, then there's probably an issue with getting the Excel add-in up and running or installed properly with your Excel. Right? And so that's something you would want to reach out to us about, and we can help assist and get it up and running. But generally speaking, we expect that when you install APS, this tab will be here and all the features and all of the functions are going to work without any issues. Okay, we're going to go into Excel, and we're actually going to show this as opposed to talking through it in the slides. So the way that you use this, you're going to use functions to pull the specific information that you're interested in into the software. And so one of the easiest way to access what functions are available is by clicking on this FX button, and it'll bring up the insert function window, and you can browse down to the bottom, pick SimCentral Excel add-in functions. Again, SimCentral is Aviva Process Simulation. It's just the old name, right? And all the functions are going to be listed here. And so you can go down this list of each function, and you can see what the function is, what it's supposed to be getting when you use it, how to go about setting it up in terms of what are the arguments for the function itself. All right, so there's a bunch of different functions here. I'm not going to talk about every single one. The main one that we utilize most of the time is going to be this SC value function. So I'm going to demo how to use that and how this works. All right, so when I choose the SC value function, what it's going to do is it's going to extract a single value from a model in your simulation file. And so when we look at this, you can see the first argument is going to be the model's name. The second argument is going to be the variable or the parameter's name. The third argument is going to be the unit of measure that you're using. The fourth is going to be the simulation's name. And then the last one's going to be the snapshot name if you decide to pull the value from a snapshot as opposed to whatever is currently in the file. And when I click OK, I have a window here where I can go about setting up the function. And what's nice about this is as I set this up, if I'm setting it up properly, it's going to start to show me the values of each of these over here. And at the end, it'll tell me what the final piece of information is going to look like. And I can check that and make sure that I didn't make any mistakes in the setup. Now, before I go through and do an example of this, I want to talk about a couple of buttons up here on the ribbon. There are 3 buttons up here on the ribbon that can be used to set a default selection while you're in this Excel file for some of these arguments. So if I click this button here, and I'm going to have to cancel to show this. If I click this button here, it opens up a window that shows me all of the files in my simulation repository, my file repository. Right? And I can browse through and I can pick a simulation for my SimCentral functions to reference for the simulation file name, right? That argument. Right? And so we're going to go, and I have Pro 1C open. I'm going to use that as my default. So I click Set Default. Now I do not have to tell it my simulation's name in that field for the argument for any of my functions. It's automatically going to use whatever I set up here. The next part is for choosing a default snapshot. If your simulation has snapshots, it'll be listed here. Right? So you won't be able to pick this unless you've set a default simulation, because it needs to reference the default simulation to be able to populate this list. And you're only going to see something if the simulation itself actually has snapshots here. Right? Mine does not. So I don't have to set anything for here. I can't set anything for here right now. And that's okay. You don't have to set a default for all of these. If you don't set a default, you either need to provide the value yourself, or in the case of like snapshots here or units of measure, it's going to default to whatever is currently being utilized within the simulation. Right? So I don't have to do anything here. For the units of measure, I can pick a specific slate. So I just need to make sure that whatever I pick has the units of measure for the different properties that I'm interested in. Now notice this slate selection is only for slates that are in my repository for my units of measure. So if you come back here and you go to units of measure here, when I pick a slate in the software, right, for a specific file, I can either pick it from the repository, which means all of my unit of measure slates for my install of Aviva Process Simulation. Every single one of my simulation files has access to these slates. All right, that's what it means to be in the repository. But I can also create slates that are specific to the simulation file. And so I don't have any created here, right? But if I did, I would have options that I can pick from here where the unit of measure slate is stored with the file. Meaning if I exported to a SimX, right, just like the information in my simulation model library, the unit of measure slate in my simulation file will be stored in the generated SimX file. All right. Now, what's important here for the Excel add-in is that you only have choices of unit of measure slates in the repository. So if you come in here and you have a slate that's saved into the simulation file and you try to select it, you're not going to be able to select it. You're going to need to first move it through the UOM slate manager, right? Make a new slate in the repository. Once you make the new slate in the repository, you can copy the slate from the simulation file to update the slate you created with the correct selections. Right, so that's how you would transfer it over. Okay, so back to this. I set a default for my simulation file name and for my unit of measure slate. I'm going to go through and set up the SC value function now. So I'm going to do SC value function. And these are the arguments again, but I don't have to put anything for UOMs or simulation name, and I don't have to put anything for snapshot because snapshot is, if I don't put something, it just uses what's currently in the simulation. So really the only two things that matter here are the model name and the variable or parameter name. So I click OK, and I'm going to start typing in those pieces of information now. So let's go over to the file and let's look at a stream here and say we're going to get this molar flow rate for stream S1. Okay, so the model name in this case is S1, and the property name, the variable name, is F. Right, so let's come back. Model name S1. Variable name F. Now, notice something. I intentionally picked the stream here as the example, the start, because I wanted to show you what happens when you type in these names like this. If the name you type in is an actual cell in the spreadsheet, S1, right here, is a cell, then it's not going to automatically update this to be, say, in quotes, right? So that it's looking at it as if it's a name within the file, right? So it's not properly getting S1 as the name of the model. It thinks it's looking at S1, the cell in the spreadsheet, right? So I just want to make sure that I put in the quotes here. And now with the quotes there, you can see it's getting the reference properly. And when you go through all of this, right, again, I don't have to supply this or this because I have defaults, and this uses, I get a value of 4,000. When I go back to the file, you can see, right, this is not in the same unit of measure state, so let me set that. You can see my value is 4,000 pound moles an hour. That's from my unit of measure state, right? 4,000 pound moles an hour. All right, so I click OK, and now I populated that value into the cell. When I click on the cell, you can see here's the function, and here's how it's set up. And I can make changes to this if I wanted to. I could change this right now. All right, so I have the flexibility to change things around. Maybe I want to make this S2 instead, which just so happens to be the same flow rate because it's, you know, the next stream coming out, right? But you can see you can make changes to it and have it update with the next value, the correct value. Now, for one specific property for one model, right? And I typed in the names of these things, which is probably not the methodology you want to go about to set up your Excel spreadsheets, right? A better way of setting this up is to use cell references. So if I do this another way, what I can do is I can set up a table, right? Let's set up a little table here where maybe I want to get a bunch of different stream properties, right? I'm going to populate out a bunch of properties for all these different streams. And I might be looking for mass flow rate, molar flow rate, temperature, pressure, vapor fraction, right? These are all properties I might be asking for out of my streams. Right, so now when I set this up, instead of typing the values, I'm going to use cell references. If I click here, I can actually pick on the cell itself where the property is. Right, so I can click on E7. I can get the variable value. That's this. That's D8. Right, and you can see it populated with the value. Right, again, it's getting the simulation and the unit measure from here. Right, so it's populated with the value. Now I've set this function up with cell references that if I am smart in the way that I go about setting this up and fixating either the column or the row of each value, I can now drag to fill out this entire spreadsheet and this entire table with all my results. All right, so I can say if I'm going to drag this down, right, I want row 7 to stay in place, right? So let's put fixation there. And if I drag this over, I'm going to want column D to stay in place. So it's those. So I drag down, you can see it populates, right? So if I look, this is S1 and W. Look at this one, S1 and molar flow rate, S1 and temperature, right? And if I go this way, populate out all my streams, right? So here's stream 1, here's stream 2, stream 3, and so forth down the line, right? So if I set up a template in my spreadsheet such that it properly allows me to reference specific properties and model names of interest, I can quickly and easily set up one function and then drag to fill out the entire table, right? This is a much more efficient way of using the Excel add-in, right? Now, couple more things that I'm going to point out here when it comes to the Excel add-in. And this is by far not the least that you can do with it. There's many different functions I didn't highlight for the sake of time. And there's other things that you can do if you want to get really fancy. You can do coding and do all the normal stuff you would normally do in an Excel file through coding and use these functions as part of your process. So you can get real creative with the things you can do in here. But what I actually just want to show real quick as the final couple points are two other ways that you can enter the functions and see how that you can go about setting these up. So obviously the one is you can always type these, right? So I can do SC, which is going to pull up all of the different Sim Central functions, right? Hence the SC. All right, so again, Sim Central, Aviva Process Simulation, same exact thing. So I could go about typing these in, and you just have to know what the arguments are, or use some shortcuts to remind yourself what the arguments are, and then just type in well, we don't want that. Type in the various arguments, and that'll be just the same as using this insert function, right? Another way that you can do it, and this is specifically for the SC value function. Everything else I've shown so far can be used for any one of the SimCentral or APS functions, but this is just for the SC value function. If you right click on a cell and you go all the way down to the bottom, you'll see Aviva Process Simulation, and it trails off here, but it should say value function, something along those lines. And so if you click it, it brings up a window similar to the one that we had when we were inserting it, where we can type in or use cell references to reference the different values. Additionally, you can click on this little icon here, and you can actually pick and choose the different properties that you're interested in. So if I click on this, you can see I get all of the different simulation files that I have in my repository, and I can just pick from the list. Right? If I click on this, I would get any snapshots available in this file. I can click on here, and I can see all of the different models that I have within the file, but not just the models, right? Here are the main models. I can see their sub-models, right? And you can take this all the way out if it's multiple embedded submodels. And so I can see the specific properties of interest in a given model by browsing the models through this structure here, right? And then once you pick a model, you can pick the variable or the parameter that you want to reference. And then once you pick that, you can pick the unit of measure, right? So you have the ability here to just make selections from lists by using this right-click option. And then when you're all said and done, unlike these, which just report the value back, you can actually insert the units of measure as well using this function. So now I have this showing here to tell me that this is in kilograms per second. All right. Some of the things I didn't show that you might be interested in with this, there are ways of pushing information. There's a function called the SC set value function, which will push a value from the Excel file into the SimCentral or the APS simulation. Right. The way that this works is you set up this function here. The value will reference to a specific cell. And then when you're ready to push the value, you click this right button, and that's going to push it from Excel into the Aviva Process Simulation file. Vice versa, if you make a change in your simulation file, and I can demo this real quick. If I make a change in my simulation file, when I come back to my Excel file, that change does not propagate automatically. I have to click this refresh button for it to update the Excel spreadsheet with the updated value. All right, so that's something else that you'll want to be aware of. There's a function in here. Oops. function in here for dynamic values. So what I was showing you already with the SC value function is for an individual value that's usually at a steady state operation, right? Or it's the final value of your dynamic run, right? But if you want some kind of dynamic result, you can use this SC dyne value function to get a specific value at a specific time increment. So t is yet just another argument here. That's your time. You would probably want to set up a template here where time is one of the things that you're referencing and all the different time increments. And then that's how you would go about setting up your template so that way you can do the referencing and quickly populate all this dynamic information. Okay. I think those are the main things I want to highlight for the Excel add-in. This here just shows you some examples of the different functions and the types of information that you can get out of those functions. Oh, one more thing that I'll mention. Excel has an ability called concatenation, which allows you to take a value from two different cells and combine them as one input for an argument in a function, right? So when I'm doing this right here, I'm referencing singular values right now. But if I go to here, and let's say I wanted to get the composition of nitrogen, right? Well, the composition of nitrogen is Z, as in that's the variable, but then there's a bracket, there's the name of the component itself, and then there's a closed bracket, right? And those are multiple parts that you have to piece together under the single argument of variable name for the function, right? And so you can't just go in here and say, the argument is, cell E1 for the Z name plus a bracket plus, cell F1 for the component name plus a bracket. There's a little bit more that's involved to make this unified as one thing, right? And that's a feature within Excel called concatenation. So what I would recommend, if you are going to try to use any sort of referencing where you're trying to pull properties that are made up of multiple parts, right? Whether that's, compositions, column, tray results, element results for multi-element models like number of tubes in a plug flow reactor and stuff like that. You have to utilize that capability in order to properly set up the referencing. All right, so we're going to leave it at that for now on that topic, and we're going to move on to the advanced topics that we're going to talk about. So the first one we're going to show is on flow sheet equations. This is a way of adding a custom calculation to your simulation that is on a simulation-wide level. It's not necessarily going to be specific to just one model or contained within a model. It's something you put into the simulation that's for the entire simulation. And while it might reference certain model properties, it's not linked to anything individually. All right. What's nice about this is that you can write all kinds of different equations here to do various things. So you can write an equation that imposes a condition that you are not able to impose in some other methodology. All right. Or you can calculate a custom property that doesn't exist within the software, right? So there might be, I think yesterday we were talking about efficiency or something with the electrolyzer, right? If you want to calculate the efficiency of your electrolyzer using variables that exist within the electrolyzer, you can add a flow sheet equation reference those variables and calculate what the efficiency will be, right? And then you can store that into a flow sheet variable, right? So there's flow sheet variables, there's flow sheet equations that can be added into the software. So that's what you're going to see me do here, demoing this and talking about this. What is nice about this capability is that it's just normal equation writing. It's nothing fancy. You don't need to do any special coding or know any coding knowledge in order to do this. If you can write a function or an equation in Excel, you can do the same thing here within your simulation environment using the flowsheet equation capability. All right, so we're going to go and look at an example of this and talk through it. So I have an example here. It's a very simple one. I already have the equation on the canvas. I'm just going to copy and delete this and revert this simulation back to one as if it did not have a flow sheet equation. So just give me a second. All right. So here's a very simple example. It's effectively a steam header. We have one turbine coming off of the header, and then we have this product stream coming off, which is representative of typical losses associated with the header. In steam balances, this is very common to have a little bit of loss on your headers, and so you can represent that by having a stream coming off of the header, going to a sink, and seeing how much is sent in the losses, and usually you're trying to minimize this to a certain amount, right? So this is a pretty standard thing. Normally the headers are much larger with many more consumers, but I've simplified it for this example's sake. All right, so in this example, we are going to try to maintain a losses of about 1% of the feed coming into the header, right? And so we have that right now. Right? If I was at a different feed, though, we would not have that, right? If I change this value, you can see this is not 1% of this value, right? So when we are setting this up, if we wanted to impose it so that there's always a 1% loss here coming out of this losses, all right, just to kind of ensure and maintain a certain balance here within the feed and loss ratio, right? What we can do is we can add a flow sheet equation. We can come over to Tools. We can drag and drop this equation model on the canvas. And when we first drag and drop it, we can see it says that it's unsquare or it's unsolved. There's an unsolved badge up here. And the whole reason is because we haven't done anything yet. It tells us the equation formula is empty. And it doesn't look like there's an area to put anything, but if you click, you can see there's this big white space here. That's where we're going to enter the equation. All right. So until you add an equation, this or add the actual formula for the equation, this equation on the canvas is just going to say that's unsolved because it doesn't know what to do with it. Right. The placeholder is there, but there's nothing guiding the software to tell it what to do with this yet. All right. So now we're going to add in. Going to be, I want my losses flow rate to be 1% of my source flow rate, right? So this flow rate, we want to be equal to 1% of this flow rate. So when I click enter, now it's using this equation. And because it now has this equation added into the simulation, the program knows that I'm over constrained, right? It treats it like any other equation. So Aviva Process Simulation is an equation-oriented solver. And all equation-oriented solvers, they don't solve by looking at individual models one at a time. They look at the entire thing as a whole, right? They say this equation is contributing these, or this model is contributing these equations And these equations are made up of these variables, right? This model is contributing these equations, and these equations contributing these variables, right? And so forth for all of the models in the simulation and all of the additional equations. In this case, we've added one more equation, right? And so it looks at this just the same as it does any other equation that a model is adding to what it's trying to solve. And it says, okay, this is one more equation, and these are the variables in that equation. And those variables are linked to this model and this model because they exist in these models. And so there are equations that tell it how to calculate those properties within the models themselves, right? And then if you take this out through all the different relationships, the program's able to know that I've added an additional constraint to my simulation. I have one too many things specified here now that I'm imposing this additional constraint through this equation, right? And so the program tells you, just as it does any other model and variable within the software, that you're overspecified and you have to remove a spec. Then you can see very clearly it identifies several different things that I can remove in order to balance the simulation again. And so I can come over here and I can unspecify this, right? And if I unspecify this, I go back to being square and solved. And now the source flow rate is going to be calculated as well as the sink, the losses flow rate, right, based on this relationship. And so whatever I end up doing to the simulation file, right, let's say I change this value here, when it calculates a new source flow rate, right, based on this value, it then calculates the losses associated with this source flow rate, right? It's linked them all together, right? And the program's smart enough to know that these things are linked, right? Because when I was on Square, it told me I could have unspecified this, right? Because it knows power helps to back dictate their flow requirement to the turbine. And if there's a flow requirement coming off of here, in order to maintain this balance, I need to then bump or change this flow rate here going into the header, right? So it knows that these things are all connected, and it can tell you what you need to do in order to rebalance the file. Now notice when I unspecified this now, and it needs me to add in a spec, I could theoretically spec the losses flow rate, right? The thing that I am trying to make 1%, right? I could give this the value and then have it back calculate the required flow rate, and in this case, the power associated with this, right? By going about it this way, specifying the system in this way. So one of the powerful advantages of these flowsheet equations is that not only are you adding in this new constraint, this new calculation, but because the program treats it no differently than any other equation in the simulation, you have the power to flexibly change what the spec is within your file and still have it impose the relationship, right? You could specify any one of these things, and this relationship will still be in effect no matter what happens, right? Now, this is an example of a flowsheet equation that is imposing a spec. It's changing this spec status just by having this in the simulation, right? But there are other types of equations that we can add to the system that don't change the specification status, right? And those are ones where you're just calculating an additional property that didn't exist before. And so I'm going to use a very simple, dumbed down example here. I'm going to add a flowsheet equation, and I'm going to calculate here the cost of this turbine, right? And now the cost of this turbine, it's not going to work out in terms of units of measure. I did not go that advanced with this, right? It's going to be really, really simple. I'm just going to say T1 cost equals And we're going to reference the power in this case. So T1 power times 1,000. All right, we're just going to say it's 1,000 times the power. That's the cost in dollars. Again, units of measure aren't going to make sense here, right? That's the cost that we're going with, right? So we click OK. And now when I look at this, it tells me that this is not solved, and it's still not solved up here. And you have to wonder, why is it not solved? And so you hover over this X, and it tells you it's missing a variable. It doesn't know what T1 cost is. That's not something that is in the simulation right now. All right, so even though I'm trying to calculate this, and it is a custom property I'm trying to calculate, I still need to have a placeholder to store the value, right? And so I need to add in a flow sheet variable that's going to store this value that's being calculated. And so I can come over here, drag and drop the variable on the canvas, and I need to tell it what type of variable it is, right? So in this case, it's going to be currency. It's going to be the dollar, right? So I'm going to pick that. Right, but I have other options that are available here. It just depends on what it is that I'm calculating. Is it a flow rate or some kind of heat transfer value like duty? Is it a hydraulic value like the liquid head, velocity, right? So you have to browse through these categories and find the correct property, right? And then you have to give it a name. And of course, you want to name it what you named it in the equation. So in this case, I want to call it T1 cost. Now, when I enter, I have a place to store the value I was calculating. All right, so now the equation's happy, and you can see what the calculated value is. Now, up until this point, this equation didn't change my spec status. All it did was calculate a value that wasn't there, and I had to make sure I put a variable in to store the value, right? But I can, just like here, I can utilize this variable as if it was a control spec, right? So I can spec this value, and through the relationship that this variable has with this equation to the other models in the simulation, the program tells me I'm unsquare, I'm over constrained, and I need to free up something. And just like before, it knows what the candidates are that relate back to this. So I can actually do this to resquare it. Now, not only is my source flow rate and my losses flow rate calculated, my power is also calculated. None of the things I had specified originally are now specified. They're all being calculated, and they're being calculated at this point based on a cost, right? So, maybe I know that I need to make this $5,000 or less. Right? So I can type in 5,000, and I can see, all right, what does that relate to in terms of a power, in terms of a required flow rate coming into my header, right? So I have the flexibility here, just like I did with any other equations and variables, to spec this and work backwards through the relationships I've added via the equations to change the way that I work with and manipulate the file. Now, a couple more things to talk about when it comes to flowsheet equations before we cap this. Over here in the Simulation Manager, one of the things that you can do is if you expand this out, you can see there's a section for all of the equations that you've added, as well as all the flowsheet variables that you've added. And this is useful because if you have a very large file and you have a bunch of these flowsheet equations all over the place and a bunch of variables all over the place, you're going to want a place that you can go to easily find this information. And so you can always go to the Simulation Manager and quickly and easily see the list of all the flowsheet variables and equations. Right, that'll make it very easy for you to find this information. All right. The other thing that I want to mention is that when you have an equation implemented, depending on the mode that you're in, when you first put the equation down, that equation is only going to be active in that mode by default. So because I'm in process mode and I added these equations, this equation is only active in process mode right now. If I switch to fluid flow mode, they become inactive. You can see that they're grayed out, strike through. They're inactive right now. So if I needed them to be active, I would have to turn them on in this mode. The way you do that, or if I wanted to turn them off, is I right-click on the equation, I go to equations, I go to mode, and you can see there's a little check mark next to each one of the modes. If it's checked, it means it will be active in that mode when you switch around between the modes. If it's unchecked, it's inactive. Now, one of the things that you can do is, let's say, for example, I no longer want to have this relationship in place, right? I don't need this equation anymore. However, I don't want to delete it because maybe there's a point in the future where I'm going to want to use it. What I can do is I can come in here and I can just turn it off in process mode. So it's still here, it's just not being used. And because it's not being used, I'm unsquare, I'm under specified, right? Because this was imposing a spec. So I do need to resquare. So nothing to be too concerned about if that happens. You just have to resquare the simulation, right? But now this is just inactive, right? I still have it, but I'm just not using it. So I don't have to worry about it anymore, right? All right, so that's everything that we're going to cover when it comes to flowsheet equations. And this is actually going to work nicely into our next topic, which is optimization. Optimization is the ability to maximize or minimize a specific variable's value. In this case, we call that variable the objective function, right? So what are we trying to maximize or minimize? That's our objective function. And this can be any property in the simulation that is a calculated property, right? So if you try to set this up and it's a specified property, you're going to get errors and it's not going to work, right? But if it's calculated properties such as anything that doesn't have a check in its box, or even flowsheet variables, right? If I had this flowsheet variable still being calculated, I could utilize this as well, right? So anything that's a variable that is calculated, no matter if it comes from a model or it's a flowsheet variable, we can use that as the objective function. And then we can set up a number of other variables to manipulate and try to affect the maximize or minimize objective, right? So we can set up variables that actually get changed. Those are going to be our primary things that get varied by the optimizer in order for it to try to maximize or minimize the objective function. And we can also have inactive variables that maybe have bounds on them, right? And so we're putting sort of an indirect constraint on our optimization, right? Tell it, you can change these values, but the solution still has to be above this lower bound for this variable, even though you're not changing this variable, right? So that's the type of thing that you can do with this variable section down here. You can work in combination of what you're changing and different bounds for the things you are or are not changing to constrain the solution and try to optimize or maximize or minimize whatever the function is that you have defined. Right. Now, the thing about optimization, this is going to be the same thing for case studies and scenarios when we get to those, is that it has a manager that you access on the ribbon. When you open the manager, you can set up multiple of these within that manager, right? So I can have multiple optimization cases. I can have multiple case studies. I can have multiple scenarios, right? So these managers allow you to set up as many as you want. And then at any given point, you can select the one you want to run and run them right from the ribbon, from the manager, or even from the editor window of the individual set. All right, so we're going to look at an example of optimization real quick. Okay, so in this file, we have a custom flowsheet equation here, and it is calculating a property called cycle efficiency. Right, so cycle efficiency is a function that's related to several different heat exchanger and turbine properties. So there's a heater duty, turbine power, main compressor power, and a bypass compressor power. Right? And we can find these models within this PFD by browsing around. So here's the heater, so the duty of this, the power of this turbine, the power of this main compressor, and then the bypass compressors over here, the power of the bypass compressor. All right, so those four properties are what are being used to calculate the cycle efficiency. And then we're setting up an optimization up here. Now, optimization is only available for process and fluid flow modes, right? So these two modes of operation, it doesn't matter which tab you access it from, it's the same information, right? But it's only in here. If you go to dynamics, there's no optimization capability here in dynamics, right? In process mode, right, when we come over here to optimization, we click this button, we can see our optimization case that's set up. And we can add more if we wanted to by clicking on this plus sign. So we have as many as we want here. When we find the one we're interested in, we click the edit button to open up the editor. So here's my editor. And in here, I'm trying to maximize the cycle efficiency. Okay. So again, I'm trying to maximize this flow sheet variable. All right. This is a calculated variable. Right. If I wanted to maximize a different property, all I would have to do is make sure it's calculated. And then I can come over here and I can type that value in. So I can type turbine. So again, we have to use our proper referencing naming. We talked about this the other day, right? It's the model name dot the property name, right? So model turbine is the model name dot, maybe DP, all right? Probably don't want to maximize DP. I'm not going to leave it like this, but this is how you would go about writing, right? So I click OK. You notice everything's satisfied. If I try to use a specified property, right, like the mass flow rate, you can see this turns red, right? And it tells me I can't do this because it's not a specified variable. So the program will tell you if you can't use it, right? Now, with our example, we're doing this cycle efficiency. So I'm going to put that back. All right, so we're going to try to maximize this value. And the way that we're going to try to maximize this value is by using these two properties here. All right, there's turbine outlet pressure. So when I come over to the turbine, there's a P2 outlet pressure variable, and it is specified. And so one of the key things about this section is that any variable that you actually want to use in the optimization, meaning you're going to change the value, right? That variable has to have this flag turned on, turned to yellow. And you can only turn this flag on for variables that are specified. If I had this as a calculated variable, right, P1 is calculated, you could see it would give me a warning here. It tells me that you shouldn't do this, right? You're not going to be able to utilize this in the optimization, right? Because the program needs to be able to change the value. It can't change the value if it's not specified. Right, so specified variables can have the flag turned on, but you don't have to have them turned on at all times. Let's say I wanted to run optimization where I only change this variable. I can turn this one off, all right? And I can still leave this in this window, all right? So you can turn things on and off over here. You can also have unspecified variables in this list here, and there's a number of reasons why you might want to do it. The first one, which is what you're seeing here, is maybe you just want to be able to see a specific variable's result directly in this window without having to go to where that variable is in the simulation, right? So the objective function, ironically, does not show you its value in this window by default. There's nothing here that shows you what the value is. So a good idea is always to add the objective function to this list as one of these inactive variables so that you can see its value right from here, from this window. Right. Another thing that you can do is you can set upper and lower bounds for any of these variables. And if you set an upper or lower bound, even if it's an inactive variable, the program must meet that requirement in order for this optimization to be successful, right? So right now, this is actually the optimized case. If I wanted to set an upper bound of 0.43, right, if I ran this again, then it's going to tweak these to ensure that this solution is 0.43 or lower, right? So I run, and you can see this change to 0.43, and you can see the values here changed accordingly. This isn't the overall optimal, right? Because if I loosened this constraint and didn't have this upper bound, it would solve to 0.45, right? But because I've imposed this upper bound, it limits the solution, right? And we can put these bounds in for any and all variables in this list, whether they're manipulated or they're just being reported back to you here in the file. So now I don't have the upper bound. If I run it again, you can see, oh, it gave a different solution. There we go. Okay, you can see it calculated 0.45 or 45%, and these are the values that got to this. Right. One of the other things I'm going to point out here, and if it wasn't obvious, this is why I'm pointing it out. We did not have to use in our optimization the variables that directly are involved in the calculation of cycle efficiency, right? You don't see me using turbine power or bypass compressor power, right? The program knows, again, through the various equation relationships, that turbine power is part of this model and that it's related to the outlet pressure, right? That these two things are linked together through other equations, right? So me manipulating the outlet pressure is sufficient enough to cause the power to change, which will then cause the cycle efficiency to change. All right, so the program knows these things. You don't have to worry about that. Right. Okay, so that's optimization. The next one we're going to talk about here is for a case study. All right. Case studies are a way of evaluating a series of changes. Typically, these are incremental changes over a similar sort of size change, right? And then seeing how those changes impact other key properties of interest. Okay, so I have an example here in this in the screenshot, and I'm just going to make this image a little bit bigger so that we can see it. Yeah. All right, so if we look at this image here, all right, what we're doing is we're varying the feed tray to a column, and we're seeing how that difference from one tray to the next impacts the reboiler duty of the same column, right? And so when it's on tray 5, this is my reboiler duty. When it goes to tray 6, the duty goes down. When it goes to tray 7, it goes down even further. And it looks like if we fed it to tray 8, that would be a pretty optimal tray to feed to because I would minimize my duty on my reboiler, right? By having the feed come in at that point. Anything past this point, it starts to increase, right? So I can see this relationship between the reboiler duty and the feed tray location simply by running this case study where I vary the feed tray location, right? One tray at a time. So once the size is 1, right? It's going to be 6 steps, so 6 trays, and I'm going to change, right? And then asking it to tell me what the effect of that change is on the variables of interest, in this case, the reboiler duty and the reflux ratio. This shows it in a plot, right? So a graphical form, right? But I can also get this information in a tabular form, which you see down here, right? And so when I look at it down here, it tells me this is case 1, case 2, case 3, case 4. You can see the feed tray location changes for each case. And then these are the associated values for each one of those changes. All right. It also tells me down here if the case solved and how long it took to solve. So that might be important information as well, especially if it doesn't solve. If it doesn't solve, then you can't really trust the results you're looking at, right? So it gives you these key pieces of information, and then you can copy this table and paste it from here into Excel. Right? So you can transfer that information over if you'd like. Right. Another thing that you can do in this case study feature is you can use a snapshot, right, to be the basis of the results that you're looking at, right? So instead of just going off of the base simulation file, you can do a snapshot as the starting point for your case study. Right, so let me see if I have a demo of this. I don't honestly think I do. I don't. So what I'm going to do is I'm just going to create one pretty quickly using one of our training files. I'm coming here. This is one of the files we used the other day to show dynamics and some dynamic related topics. What I'm going to do here is I'm just going to increase the flow in the source and then see the effect that it has on the product flow rates, right? We are assuming the split ratio in the drum is going to be pretty much consistent. So we should see a pretty steady increase in both of these values as we increase the feed flow rate. Right, but this should be a pretty easy one to set up, and I suspect it will work just fine. All right, so we're going to come up here. We're going to go case study. This is the manager. We're going to add a new case study. All right, we can give it a name and description. Click edit to start setting this up. And we're going to set it up for source 1 mass flow rate because we want to be able to change a property that's specified, right? We can't change a property that's calculated, right? So it's going to start off with a minimum value of, this says 310,000. So we'll say 310,000, and we'll say this is going to go up to 400,000. And we're going to do 9 steps of 10,000 pounds an hour each. And so you'll notice when I typed in 9, it automatically told me the step size for each one of the changes over this range. So I didn't have to type that in. All right. And we're going to ask for this to show me the impact on sync 1 flow rate and sync 2 flow rate. Now notice when I type, and this happens in a lot of these different windows, you saw it in the optimization window, you see it here with case studies. There's a lot of windows where this happens. A lot of fields where you're referencing a specific property, as you start to type, it will start to filter the list based off of what's available to you from what you're typing. All right, so this also makes it a little bit easier to find the properties of interest and perform your data entry and setup. Right, so I have this set up now, and really it's as simple as that, right? As long as I have, trying to find a nice place to put this. As long as I have the thing that I'm changing, and this could be multiple things, right? Like I could have added more things that I changed from one case to the next, right? But as long as I have the thing that I'm changing and the things that I want to look at for the results, I'm good to go. And so now I can run this. And it goes through, and it went really quick because this is not a complicated change. You can see every one of these took 12 or less milliseconds. So it did not take very long to run this case study, right? Or actually 16 for this one, right? And you can see here are the results, right? So this is the value that it changed from case to case. And then this is the change in those product flow rates from one to the next. All right, and if I wanted to, I could copy this table. We'll see, come over to Excel. Paste. All right, so it's easily transferable over into Excel from these tables, and I can also show the plot. And when I click show plot, I can actually tell it what I want to be looking at. Right, so once I pick a couple of things and I have at least something on a bottom axis, it'll start to show me the plot. Okay. And then this does not have an export option, but you can always take a screenshot of this. All right, so I mean that's really it. It's a pretty straightforward capability. Just like optimization, this is only available in the process model library or the process mode and the fluid flow mode. Right, so you will only find this under those two modes. You're not going to find it in dynamics. Okay. All right, and then the last topic we're going to talk about today is scenarios. Scenarios are, in a way, the equivalent of optimization or case studies for dynamic behaviors, right? So a scenario is a way of scripting a series of changes that you can then repeat over and over again whenever you run the scenario. They don't have to be just for dynamics, but they're traditionally used in dynamic related cases. All right, so case studies here is actually a new feature in one of the latest versions of APS. Prior to this being added, if a user wanted to do something similar to what this case study did, they could theoretically do something with scenarios where they script a series of changes and take snapshots in between each state, each change. So it would be make this change, take this snapshot, make this change, take this snapshot, and then they can go back and load each one of the snapshots to see what the results are at every one of the changes. That was less than ideal for case studies, at least the way that most people want to do case studies, because a lot of times you're constantly loading different snapshots just to see one or two values. It's a very tedious process, and the setup of the scenarios is often very tedious. So it's not necessarily something you want to be using for steady state modes of operation too often. Typically, what you do is you'll use these scenarios in occasionally some of the steady state modes like process mode or fluid flow mode to set up what's going to end up being run in dynamics. And the real benefit of scenarios tends to be in the ability to run dynamics for specific lengths of time or until certain conditions are met, and then make changes and then continue running and cycle through these things while automating this sort of dynamic run behavior. And by doing that, when you have these dynamic scenarios recorded, what's nice about it is that now at any point in time, you can replicate the exact same behavior that you had in that dynamic run as far as to exactly how long you run, exactly when you make a change, and so forth over and over again simply by running the scenario. That's useful because sometimes trying to replicate behavior in dynamics can be difficult to do manually, right? Just think about this. If I said, run this file in dynamics for a minute, make this change, and then run it again for another minute, right? When you go to stop at the 1 minute mark, you are not a computer. You're not going to stop it at exactly 1 minute, right? And so you may stop it at 59 seconds. You may stop it at 1 minute and 3 seconds, right? Because of just your reaction time clicking the pause button, right? And so what happens is every time you have something like that where you have to stop and make a change and you're not exactly dead on every single time you do it, you get variance in your dynamic run. And that variance can lead to different behavior. So when you're trying to tell someone, look at this behavior that I'm seeing in dynamics, and you can't replicate it because of manual discrepancies from one change to the next, right? That's going to make it difficult to show the behavior you're trying to get across. So that's where scripts come in, these scenarios, right? You can have a series of steps that get carried out exactly the same way every single time. And you can always go back to it and rerun it at any single point, right? So that's the purpose and benefit of scenarios. We're going to look at an example of one and show you how to go about using the scenario interface. This is actually going to be the same file, but a little bit later when we add in some depressuring and blowdown scenarios, right? So these are just trends that show those results of interest for those different scenarios. But you can see up here, we have the scenarios defined, right? So to use scenarios, you can go into any one of the tabs, right? Process, fluid flow, or dynamics. You click on the scenario manager button to open it up. You can have as many scenarios as you want. So as you can see, this file has 2 already set up. And we're just going to look at this first one for depressuring. Right, so we click that, we click edit. When we look at this list here, we can see that some of the things that the scenario can do are take revert snapshots, set values for specific properties of interest. We can swap specs, so we can specify a value and then calculate a different value. We can run for a set amount of time. In this case, it's 5 seconds. We can then change a value during the run and then continue running for another 5 seconds, right? We have the ability to change things as a ramp, right? So I can run from this value to this value over 20 seconds. And so the first 20 seconds of this 60, when I tell it to run for 60 seconds, it's going to be changing this value up to 0.7, ramping it up, right? And then I can run it out, and when I'm done, I can save another snapshot. All right, so that's what this scenario is doing. And then once I have this all set up, I can run it at any point in time. So if I look at this right here, all right, here's my trend for my depressuring behavior, right? And you can see results that are currently in the file. If I run this, we're going to see these results changing and this trend being built out because it's replicating and rerunning all these steps that you see here. So it's going to run the dynamics over again, right? Now, the thing to know about the scenarios is that when you run them, they will always run in fast mode, right? So it's trying to get through this as quick as possible. So even though I have things here that add up to about 110 seconds, when I click run, this is going to take all of about 3 seconds to run. All right, it's not going to take very long at all. All right, so it's not running in real time. It's going to run in fast time. So let's keep an eye on this. You can see how this gets plotted out, and you can keep an eye on some of the results to see how those things change as well. Okay. So this is the behavior I got. These are the results I got. If I wanted to, and I click this again to rerun it again, I get the same exact behavior. If I run it again, I get the same exact behavior, right? That's the benefit of scenarios. You get the exact same behavior every single time. Now, I'm loosely saying that because I didn't change anything, right? This here has certain steps that don't change. That's the thing that's not changing, right? But I could have made changes to my simulation file that, had I not reverted this snapshot to start with, which is common when you're using snapshot or using scenarios, is to revert a snapshot so that you have the same behavior. If I didn't revert this snapshot and I had different results every single time, then it's going to change the behavior. It's not going to be exactly the way that we're saying it here. All right. So when I say you get the same behavior every single time you run it, that's a little incorrect. It just means that we get the same steps being replicated, right? But the results could change if we're not careful in the way that we go about setting this up. Now, if we wanted to set up a scenario, the way that we would go about doing it, and I'll create a new one here just so we can see it. Typically, what you want to do is just click this record button. And once you click this record button, everything you do in the file, everything you do is captured in here as you're making changes. Right. So I'm making all these different changes and it's capturing that information here. This is going to be the easiest way for you to set it up. Right. And once you're all said and done and you're happy with the changes you made, you click stop. And then what you can do is you can come back and you can edit this. Right. Maybe I didn't want it to run for 1.8 seconds. In reality, I wanted it to run for a minute. Right. So I can just edit this. Maybe 1200 wasn't the exact value I needed. I needed 1500. Right. So I can change everything that's in this table, but getting it set up, the infrastructure essentially, is easier to do by recording and then making the changes that I want to make and then just stopping the recording. If I want to make things, if I want to put things in manually, I can click this plus sign here to add in a new command. And then I can click on the pull down and choose what it is that I'm trying to do. Right. So in this case, do I want to do something that's related to a variable or parameter, such as changing a value, swapping a spec, something along those lines? Do I want to take or revert a snapshot? Do I want to change the solver? If it's manual mode or automatic mode, do I want to run or solve the file? Do I want to run in dynamics? And their run actually has many different options here for how you run. So run for a certain amount of time, that's what this was. But you could also do run until a certain timestamp. You could do run until a certain variable value, right? So run until the, I don't know, the temperature in the drum is above negative 64 degrees, right? So that's an option. I could run until steady state, right? So there's different options here that are available for my run. I can switch modes and I can even run other scenarios. So a scenario can run another scenario, which is pretty interesting. We actually utilize this a lot when we do demos at conventions because you want to always show the software doing something. And you could set up a demo that basically cycles or set up a scenario that basically cycles with other scenarios and just constantly keeps the program looking like it's doing something, right? So there's some really interesting things that you can do there by triggering other scenarios within an existing scenario. If you're ever unsure of what these commands are or even the arguments for these commands, you can go to the help and you can search. Again, as I mentioned on a prior session, due to a bug, I don't have the search field, but there's a search field usually up here, and you can type in scenario commands or something along those lines to find what the different commands are. Give me 1 second. I'll try to find them through the old-fashioned way. All right, so it's called understanding command arguments. All right, so you'll get this this help document here that shows you what all the different commands are and all the different arguments that are available to you for those commands. So this gives you a list of all the different things that you can do. Zoom down. There we go. All the different things that you can do with these commands in the scenario window. Okay, so that's everything for today. For the first time, we ended early enough that we can do Q&A before the end of the time frame. Last little bit that I'm going to say before we do the Q&A is there are different ways that you can get help. We've talked about this before. You just saw me in the help window here. There's also model-specific help, which we've talked about in length. So go to this to get more information as well. There's always the editor windows, which can tell you more about how certain things are being calculated. That's always a good reference point. Down here, this is our SimSci support email address. You can also open up cases through our support website. If you do go to the support website, you will have to register in order to log in. A lot of times when you go to our support website and you're trying to register, it might ask you for something like a company name or your company email. Don't be thrown off on that if you are a student or work with the university. Use your school information as if it's a company, right? And that should be sufficient. And same thing here, this is just like if you do reach out to us for support, this is the kind of stuff that we're looking for. Typically, when we look at a case, instead of company, just give us your school name, your school information, right? That's really all we need. And then there are other areas that you can go within that support website that you can get some assistance, such as FAQs, training links, examples, and so forth. And so there's a lot of information in these support sites. And with that, let's open it up for Q&A today. Okay. Up to now, I have been using Pro 2. Aviva simulation software offers more possibilities. Is there any functionality in Pro 2 that cannot be realized in Aviva process simulation? Okay. Pro 2 is our legacy long-term flagship product. It's mainly for steady state heat material balances and design calculations. It has a history of supporting our refining customers and the refining industry. So some of the things you're going to find in Pro 2 that you won't find in APS right now are a lot of those refining specific capabilities, right? We don't have full-blown distillation stream support, assay support right now in APS, but Pro 2 has that, right? We don't have refinery inspection properties, but Pro 2 has that, right? Interconversion methods for assays, right? A lot of this does relate back to assays, but there are some other things for specific types of processes where we don't exactly have the thermo methods implemented or the unit operation capabilities that would be required for those processes that are typically supported in the refining sector that Pro 2 already has and supports. Off the top of my head, pump arounds on a column, right? You can do a pump around, but you're going to have to manually simulate that. The column model itself doesn't automatically have a pump around. Same thing with side strippers. You could simulate them with another column model, and it's easy enough to do, but we don't have a side stripper that just automatically attaches to the column model like you would in Pro 2. Right, so those are just a couple examples. Generally speaking, when it comes to the chemicals industry and especially with renewables and some of these other areas, one that we're getting into right now is wastewater treatment. Pro 2 doesn't have those at all. With APS and the development philosophy of APS, and when it first came about, we intentionally went into industries that our other software was not supporting or not supporting well. All right, we were trying to break into new markets. And so a lot of that stuff that you can do within Aviva process simulation is very strong for the industries that we support. And as you'll see with this academic competition, allows you a lot of flexibility and functionality for the competition problem purposes and the industries that this competition problem is supporting. Right? But generally speaking, when you start to branch outside the things that we are supporting, that's when you start to see limitations where other software like Pro 2 might have an advantage because that's where those programs have been focused in the past. Hopefully that was sufficient. Is there any link to the APS software installation for people who are taking part in the competition? Bruna, I'm gonna let you.
We will send all the information to all the registered participants with the link to download about the license and also about those recorded videos. So you will receive an email with all the information.
In optimization mode, can we see the previous value of a variable and compare it to the current value? Also, can we add a step change along with lower and upper bounds? Okay. You would want to take a snapshot first before you run the optimization, and that would allow you to revert back to the snapshot and see the previous values. And you can also take a snapshot after the optimizations run, so that way you can see the optimized values. And then you can do a comparison between the two for the key properties that you're interested in. That would be the way that I would go about comparing the two. You could always write this information down, right, manually. But if you're looking for something for the software to do that, you're going to have to utilize snapshots to be able to retain and then switch back and forth between the different sets of results. When it comes to a step change, there is a settings library that you can import. So let me show that real quick. You have to be a model writing role to import libraries. Okay, so go to model writing, come over to here, go import library, go to our examples folder here, and you'll see a settings library here. Now, I believe I already have it imported, so I'm not going to try to import it again. All right, but you would need to import it. I am just going to show it because I already have it imported. Once you have it imported here, there are different models that you can add to the canvas that have various settings for the different types of solvers that you see here, right? And so one of them is an optimization settings model. You place it down, and then you do have the ability here to change different optimization settings, some of which may be able to limit step sizes, or other sort of like tuning parameters when it comes to the optimization solver. If you want more information on these different methods and what they are, what they mean, what various values mean of those, you can right-click on the settings model in the model library and go to help, where a lot of this is documented. All right, so you can see what each of these means, what the typical values are, what values mean, and so forth. This would be the closest thing available to you to putting in, say, a step size limit. Otherwise, the only limit in the optimization is the bounds themselves, right? So whatever bounds you end up putting on here, that's just the limit, but it's not changing how big or small of a step size it takes from one change to the next. Okay, that looks like the last question. Is there any other questions that anyone has that I can help with for today?
Okay, I think we can end the training session now. There
Yep.
is no more questions. So tomorrow, as we told you, it is an optional session. The topics will not be part of this competition, but for everyone that wants to know a little bit more, please join us at the same time and same link.
Yep.
Okay, so thank you.
Thank you, everyone.
Bye-bye.
Bye-bye.